Hello my dears, how are you all? So I couldn't make video yesterday, that's why you didn't receive it. Okay, so I have some personal emergency, that's why. Okay, anyway, what about your studies and all? For electrical inspector examination, I think 2 months are there. June 29th. June 30th, right? June 30, I think the exam date. So those who are preparing for that examination, please make your preparation faster, and within a span of 1 month, please try to complete everything, and after that, the remaining 1 month, please try to solve the previous year question paper. Okay, topic wise or subject wise previous year question paper you have to solve. And for those who are preparing for sub-engineer as well as assistant professor examination, time is there. The dates are not till came, so relax. The same, study in your own way. Okay, until the date come. So relax and study. Okay. So today we are going to deal with thermal power plant. So yesterday we dealt with what? Hydroelectric power plant and some factors, right? Load factor, diversity factor, etc. That's very, very important. So now thermal power plant. Thermal power plant. So I will draw a schematic diagram of thermal power plant, my dears. That is very, very important. Just you remember this diagram, that's all. Just a schematic diagram, idea, schematic. Just to draw this, my dear. Just to draw this schematic diagram, and I will explain one by one. Just to draw this, I will explain one by one. So in the diagram, see, my dears, thermal power plant means it's nothing but the final step you need is you have to rotate the alternator. Then only electrical energy will be delivered. Okay, you have to rotate the alternator. See, suppose this is our alternator. This is our alternator. This is mechanically coupled with anything. Anything it can be mechanically coupled with. It may be a turbine, or it may be another motor, anything. So normally we are in large power station and all, in power generation system and all, normally we are employed with a turbine. So turbine, it is coupled with the generator. So our aim in all three power stations, whether it is hydroelectric, or it is steam, or it is nuclear, our primary aim is what, my dears? We have to rotate the alternator, or we have to rotate the turbine. The force required to rotate the turbine, depending upon that force, the three power stations are normally classified. if the rotating power is, the rotating power of the turbine is provided with water humming or the water kinetic energy, then it is called the hydraulic power station. If the rotational power or the energy required for the rotation of the turbine is from steam, is from high pressure steam, my dear, high pressure steam, then it is called the thermal power plant. It is called the thermal power plant. So what is the simple layout of the thermal power plant means? Basically the main important function, the main important component of a thermal power plant is nothing but boiler. So what does a boiler do? What does a boiler do actually? So a boiler do, it convert the water and heat into a high pressured, high temperature steam. High pressure, high temperature steam. The technology that we are using nowadays for the thermal power plant is supercritical temperature. Supercritical temperature. That means in this we are boiling the water up to 600 degrees Celsius with 30 Newton meter per mm square. This much pressure you are going to apply there. This much pressure you are going to apply there in the boiler. So the steam obtained after boiling the water is with this much capability, 600 degrees Celsius with 30 Newton per meter square. And it is connected to superheater. This is nothing but, my dear, superheater. The function of the superheater is to remove the vapor from the steam, because if it is directly hit with the turbine blade, the turbine blade gradually starts corroding. The turbine blades gradually starts corroding. Why? Because it's steam, it's water content. Is it clear? And for avoiding that, what we are using is superheater. So superheater, what it does? It eliminates the vapor from the steam. So after this superheater, my dear, it will be only a high pressured air. It will be only here we will get a high pressured air. So that high pressured air is hit to the turbine, so that the turbine smoothly runs with very high speed, and that there will be an alternator which is coupled with the turbine. That also we can. This is our alternator. This is our alternator, and we will get a three-phase supply. We will get a three-phase supply. And of course, to work the boiler, for the working of the boiler, we need coal, right? A fuel should be there in order to boil something, right? A fuel should be there in order to boil something. So that fuel is nothing but coal. That fuel is nothing but, my dears, coal. And there will be ash as a byproduct of the boiling process. So the ash can be collected and it is removed to the ash handling plant and it is transported away. And there are two important components here in the boiler, connected to the boiler. One is economizer and another one is air preheater. One is economizer and another one is the air preheater. What is the function of economizer as well as the air preheater? These two having similar function here, because the gas, right, this is the steam that gone, and there will be a gas which is the residual of the boiling process. Of course, no. Suppose you boil something, there will be gas, of course, and there will be heat. That is the byproduct. And another byproduct is nothing but the gas. That gas you have to release to the chimney to very high height, right? To very high distance, you have to remove that gas to the atmosphere. So it is directly go to the chimney. So in between, it is go to chimney. There are economizer as well as air preheater. This APH is nothing but, my dear, air preheater. Its name is what? Air preheater. And what is the function of air preheater and economizer? I will tell you. This gas, this is called a flue gas, my dear. FLUE gas, flue gas. The flue gas contains a lot of heat also. This flue gas also contains heat, my dears, because it is directly come from the boiler, so it contains heat. So that heat you have to utilize, right? So that heat is absorbed by the economizer and it is again fed back to boiler, so that its efficiency will again increase. Air preheater is doing again the same function, my dear, again the same function. The heat absorbed from the flue gas, that is after the absorption of heat, there are also some heat which is trapped in the flue gas, that is also collected by air preheater. So the economizer as well as the air preheater do the same function, my dears. What? To absorb the heat from flue gases and it again fed back to boiler, so that the efficiency of the boiler can be increased. And the remaining gas, right, it contains carbon dioxide, carbon monoxide, methane, ethane, etc. And it is not contain any heat. It is simply a dry air. That dry air is go to chimney and it will go to the upper atmosphere. So that is the working of a thermal power plant. That is the working of a thermal. That's all. So here in the cold, right? But we are dealing with cold now. Suppose we are talk about cold. So there are 4 types of cold, my dears. Peat, bituminous, lignite, anthracite. So this anthracite, right, this is the best quality coal, and peat is the worst quality peat. And in this thermal power plant, we are using lignite. We don't get anthracite because peat, bituminous, lignite, anthracite is very high quality as well as high costly coal. So we are using bituminous. Suitable for thermal plant. So we are using the lignite. So suppose a one-word question may be asked, what? Which is the best quality or which is the worst quality coal from the following or among the following? So there may be a chances of asking that type of question. So that's why I did. So that's all about the what? Okay. Is it clear, my dears? Is it clear? And there is one more component actually. After this, condenser. What this condenser do means, after this is the pure vapor, not pressurized air. So this pressurized air, after hitting the turbine blades, is collected by a condenser, and the condenser again convert this gas to liquid, and it is again fed back to this is, you can also write coolant. Condenser, or it is goes to coolant and it is again fed back to the boiler. That's all. Sometimes the condenser also do the same function. It condenses as well as cools. You simply avoid this step. It simply condenses. The condensation process itself contains the cooling also, and that cooled water is again fed back to boiler, so that again the water can be utilized somewhere. That's it. Okay, my dear. So that's the working generally. Normally this type of it is actually not in your syllabus. For AE, JE examination syllabus, it's not there, but chances are there for asking some question. That's fine. Is it clear, my dears? Next one, nuclear. Nuclear power plant. The same thing, my dear, there is no need to draw the diagram and all, because you know this, right? Already know this. So I will just recall the knowledge you have already. So nuclear power plant is nothing but we are using, that means anyhow we have to rotate the alternator. For that we have to rotate the turbine. For that we need some form of energy. In the thermal power plant we used what? The high pressure vapor, right? Steam, correct word, steam. We used it to rotate the turbine. So for the steam, that means for convert that water into a steam, we need a boiler, cold and a heat arrangement, so that it convert the water into steam. Remove that boiler section, my dears. Remove that boiler section. That heating purpose is done by the nuclear reaction. Then it is called nuclear power plant. So in the nuclear power plant also, the same procedure which is very much similar to the thermal power plant is happening, but there is this difference is that now we have to manually heat the boiler with coal, and there will be chimney arrangement all. But in nuclear power plant there will not be any boiler. Instead of that, the heat is generated by the nuclear fission. Our correct word is controlled nuclear fission. What's, my dear? Controlled nuclear fission is the process in the nuclear power plant. So, of course, we know India is rich in thorium. Rich in thorium, not uranium, my dear. Not uranium. India, you write India, rich in thorium, not in uranium. That you have to notice. So thorium is the fuel for nuclear power plants in India. Thorium is the fuel for nuclear power plants in India. And what are the components of the nuclear power plants means? Components. Briefly I am saying, my dears, not deeply. First one, reactor core. So the reactor core consists of, my dear, reactor core consists of zirconium rod coated with aluminium, filled by thorium powder inside. Filled by thorium powder inside. That means it's nothing but, my dear, there will be a rod which is made up of zirconium, and inside that there will be pellets of thorium. Zirconium rod, there will be pellets of thorium inside that, and that will be the reactor core, and there we are providing the what? Material for fission, right? Material for fission. And moderator. Heavy water plus graphite is used as the moderator. The function of the moderator is to slow down fast moving neutrons. You all know this, right? You all know this. That is the moderator. Next one, control rods. The function of the control rod to absorb extra neutrons and control the chain reaction. Control the chain reaction. Here we are using boron, cadmium, hafnium. So these are the material we are used as the control rods. Okay. Next important is the cooling. So we can use air cooled, simply gas cooling, liquid cooling, or solid cooling, or metal cooling also. Solid instead of metal, metal cooling. Gas cooling means you can use hydrogen, carbon dioxide, helium, etc. And liquid cooling means heavy or light water. And this metal cooling means molten lithium or sodium. You can use as the cooling for as a molten cooling. That's all. Simple. Okay. And there will be another component is biological shielding. You know this, why? To protect it from, or to protect the environment. To protect the environment. That's all. So this is the brief knowledge about the 3 power plants, my dears. 3 power plants. Please note it down and just study this one. Not much more. Just study this. Okay. It is more than sufficient. It's more than sufficient. It is more than sufficient, my dears. Next one, comparison. So you draw a table. This is very, very important, my dear. Just read the table. That's all. Read this table. That's all. Hydro, thermal, nuclear. Hydro, thermal, nuclear. Just read this table. That's it. Just write, my dears. Some points I am going to write. Very far from load center. Near the load center, but transportation similar near the loads. Just write that. Okay. long away from population. Another point, most simple, comma, no air pollution. Less clean, due to ash handling. Difficult dispose nuclear waste. Quick starting time. Five to 20 minutes. 2 to 3 hours. 2 to 5 hours. High efficiency. 80 to 85%. Efficiency equal to 30 to 45%. Again 30 to 45%. Plant life 30 to 50 years. 20 to 30 years. 20 to 30 years. Operating cost very less. Very high. Moderate. High initial cost. Very high. Initial cost always. Initial cost low. Alright. So these are the important comparison, my dears. These are the important comparison for hydrothermal as well as the nuclear power plant. So for examination point of view, you just note this. Quick starting. Which power plant? Hydro. High initial cost. Least operating cost. High initial cost. So high operating cost. Sorry, high operating cost. Operating cost is very less. Very high operating cost. And that's efficiency. You focus on these bubbled points. It is more than sufficient. It's more than sufficient. Comparison. Okay. Comparison. So that's all about the comparison areas. That's all about the comparison. Did you get the points? Did you get the points, my dears? Did you get the points? Okay. Next, transmission line. parameters. Transmission line parameters. See my dears, our transmission line, right? Our transmission line, right? So power you generated, right? Power system means it contains the generation, transmission as well as the distribution. That is the total power system means. So we dealt with the power generation. Now we have to distribute the power, right? So for distribution of the power, we have to consider the transmission line. We have to consider the transmission line, and we have to know the clear knowledge about what makes the transmission line actually. What makes the transmission line actually, or what are the losses in the transmission line, or how difficult to carry the power through the transmission line. That all things we have to know before we are transmitting or transmitting the power. Okay, so first thing, what is actually a transmission line means, what it comprises of, that we have to know. See my dears, so the transmission line, I can tell you one thing. So this is the simple transmission line, a simple transmission line. There will be a line and there will be a neutral. We know that a conductor, this may be aluminum conductor, or normally it is aluminum conductor, right? A conductor consists of, my dear, as a resistor as well as the inductor as well as the resistor. So it is comprises of what? A resistor, inductor combination. Here also what? A resistor, inductor combination. And see my dear, these two conductors, right? These two conductors carries current, of course. This carries plus and the return path is carried by the neutral. So if two conductors are separated by air, right? In the transmission line, you see the transmission line, right? So neutral, phase and neutral, in between there is an air. So if two conductors are separated by an insulating medium, will form a capacitor, of course, right? Form a capacitor. So there will be a capacitor. And of course, there will be, see my dears, there will be one term I am going to represent called leakage current. Leakage current. That leakage current is nothing but, my dear, see, this is the tower. See, this is the tower. This is the tower in which we are sending the transmission line. Okay. So the tower is now, it is earthed, right? It is earthed. Okay. Here, through an insulator, we are supporting a conductor, but the insulator is not vacuum, right? Not perfect vacuum. So there will be a chance of flowing. Current from line to insulator and to earth. That current is called the leakage current in a transmission line. Also, the air, right? This is air, right? There is a small current across the air also, because the air also conduct. It is not a perfect insulator. The air contain humid and all. The air contain dust and all. The air contain water droplets, and also there will be a small current which is crossing this insulator. I mean the insulating medium also. So in short, my dears, there will be always some leakage current in the transmission line, and that leakage current is represented by the conductance G. See? So in short, our transmission line is equivalent to distributed network consists of R, L, C, G. Very important. What are the line parameters means, my dear? What are the transmission line parameter consist of means? Resistor, inductor, capacitor and conductance, where G is called the conductance. That means the leakage current is represented by conductance G. The leakage current is represented by the conductance G. Okay. So our primary importance of finding inductor as well as the capacitance in a transmission line, that is very, very important, because that actually play a vital role in the performance of the transmission line mediums. Not resistor, not conductance, but inductor as capacitor play a vital role in the performance of the transmission line, or in the performance, or in the stability of the transmission line, or many things, okay, velocity of propagation, many things we are going to deal with according to L and C. So now we are going to find the expression for the inductance of single phase as well as three phase transmission line, capacitance of single phase as well as three phase transmission line, and many more. Okay, so I'm going to derive the expression for inductance of a single phase transmission line. Inductance of a single phase transmission line. Okay. Listen, my dears. So this is the transmission line containing L and N, its cross section. The conductor radius R is the radius of the conductor, and D is the distance between the conductor. Plus IE means a directional current is flowing here, and a return path is flowing outside, that is through the neutral. Minus I is meaning that it is a return path. Okay, my dear. Not mean that it's a DC, but it's a instantaneous value, and which is nothing but the return path. See, my dear, the inductance of the transmission, single phase transmission line is actually contributed by inductance L total is nothing but, my dear, L internal plus L external. L internal plus L external. That means, I will tell you, focus on one conductor, focus on this conductor only. The total magnetic field associated with this conductor is by 1 due to its own current inside, due to its own current outside, due to the neighboring current outside. So these are the three magnetic fields experienced by a single conductor. One, I will say once again, see, I am a conductor. Electric field inside me is 0, but not magnetic field. I will remember you. Okay, I will remind you one thing. You already studied electric field inside a hollow conductor will be 0, but not magnetic field, my dear. So the effective magnetic field, suppose me and you are two conductors, you imagine. So what is the total magnetic field felt by me means? One, the internal magnetic field. Okay, second one, there will be some external magnetic field by myself also, right? And that is again linking with me. See, my dear, this is a magnet. So the magnetic field means, see, this is the internal magnetic field, as well as this external also. There is an effect on this now. That's why. So the internal magnetic field plus the external magnetic field due to myself plus the neighboring conductor current carrying now, that flux also links on me, right? So there are these much fluxes on me, or these much magnetic field on me. So there are two types of inductors, my dear. One is L internal and another one is L external. The value of L internal is nothing but mu 0 divided by 8 pi. Mu 0 divided by 8 pi. Mu 0 divided by 8 pi is the value of L internal Henry per meter. So by looking this expression, the internal inductance is only depend upon, my dear, mu 0, where mu 0 is nothing but 4 pi into 10 raised to minus 7 Henry per meter. 4 pi into 10 raised to minus 7 Henry per meter. Okay, that is called the, what is that? Absolute permeability. Absolute permeability or permeability of air. That's all. Permeability of air. And L external, right? L external. There is a very big derivation for L external, but we don't want that derivation. We just need the equation, my dear. 2 into 10 raised to minus 7 ln d by r Henry per meter. This is the equation for L external. 2 into 10 raised to minus 7. You just remember these two equations, my dear. Enough. So L internal means the internal inductance plus the external inductance, which is nothing but 2 into 10 raised to minus 7 ln d by r. Combinedly, if you combine this together, my dear, we will get the L total is equal to, what is that? 2 into 10 raised to minus 7 ln d by r dash, my dear. D by r dash, because we merged this mu 0 by 8 pi into this equation, so that this r become r dash, where r dash is called GMR or effective radius. Its value is 0.7788 r. Its value is 0.7788 r. GMR is nothing but geometrical mean radius, which is nothing but 0.7788 into r is nothing but the GMR. That's all. So in terms of GMR, finally we have the equation L total will be equal to 2 into 10 raised to minus 7 ln d by r dash Henry per meter. That's all. This is a single line inductor. This is a single line inductor. Inductance due to this line only, but only not this line contributing the transmission line of a single phase. 2 conductors are there for a single phase transmission line. So instead of this single line, this is per phase now. Henry per meter, this is per phase. So loop inductance is nothing but L loop is equal to 2 into L per phase, which is nothing but, my dear, 4 into 10 raised to minus 7 ln d by r dash Henry per meter. Very important. Very important. But that's all about the single phase transmission line inductance concept. You just want to know this, not more than that. Okay, there is a very big proof for the derivation, but we don't want, we just need the equation. That's all. We just need the equation, my dears, not more. Okay, so the total inductance of the transmission line is nothing but, my dear, loop inductance. That means loop inductance. This one plus this one. That is nothing but 4 into 10 raised to minus 7 ln d by r dash Henry per meter. That's all. If you have any doubt, if you have any, my dears. Okay. Three-phase line. Three-phase line means there are two possibilities for three-phase transmission line, my dear. First one is unsymmetrical spacing. Second one is symmetrical spacing. I will tell you one by one. First of all, we are going to deal with unsymmetrical spacing. First of all, we are going to deal with unsymmetrical spacing. So unsymmetrical spacing means the distance between the three phases, right? The three phases of a transmission line will not be same. Unsymmetrical means what, my dear? The distance between three transmission line will not be same. Will not be same. For example, this is one conductor. This is another conductor. This is another conductor. Okay. Suppose this is A phase and this is B phase and this is C phase. Distance between this is D. Maybe distance between these also D. But distance between A and C not D. That is called unsymmetrical spacing. Or another case, this is one conductor. This is one conductor. This is one conductor. The distance between this and this may be D. Okay, very good. The distance between this and this will be also D. But distance between this and this will not be D. It is 2D. So there will be unsymmetrical. There will be unsymmetrical. So that is the meaning of unsymmetrical. Many cases are there. Just two cases. Okay. So what will be the inductance of an unsymmetrical line that we are going to discuss. So the equation for the inductance per phase, L per phase, because three phase line, right? So always we are calculating per phase. Unless it is mentioned, find the loop. You just always think that it is a per phase value, it is a per phase value. Okay. So inductance per phase will be, again my dear, 2 into 10 raised to minus 7 ln GMD divided by GMR. That is the equation. Henry per meter. Henry per meter. This is the equation for the unsymmetrical space. Or more unsymmetrical three-phase line. Simply the inductance for a three-phase line is nothing but 2 into 10 raised to minus 7 ln GMD divided by GMR. I will tell you what is GMD. GMD means distance with others. This is a short form. Distance with others. GMR, self distance or self radius, simply self radius. Okay. For this arrangement, unsymmetrical spacing, this arrangement, my dear, what will be GMD? I will tell you. It will be more and more clear to you. GMD with distance with others. See, my dear, for finding the GMD of this type of spacing, focus on the conductor A. Distance with other, B, not it down, D into distance with other, D plus D, 2D. Okay, one term into, focus on the second conductor B. Distance with other, D, distance with other, D, second term. Next, focus on the third conductor, distance with other, D, distance with other, 2D. How many terms are there? 1, 2, 3, 4, 5, 6, raised to 1 by 6, that's all. Raised to 1 by 6, that's all. That is the GMD. That is the GMD. So by solving this, I will get, my dear, 4 raised to 1 by 6 into D, 6D na, D raised to 6, whole raised to 1 by 6. 4 raised to 1 by 6, nothing but 1.26. And D raised to 1 by 6 and 1 is cancel, simply D. So GMD will be equal to 1.26D. Very, very important. Very, very, very important. Very, very, very important. Okay. And for three-phase transmission line, my dear, what is GMR? What is GMR? It is self-radius. Self-radius is nothing but, my dear, 0.7788 into R. Simple. Or simply R dash. R dash. So now you got GMD and now you got GMR. Simply substitute this, you will get the inductance. That's all. Simply substitute, you will get the inductance. Is it clear? Is it clear, my dear? Okay, and what about this arrangement? Let's check that also. For examination, my dear, any type of unsymmetrical spacing may be asked. You have to do the correct thing. So for this, what will be GMD? Let's check. GMD. Focus on conductor A. Distance with other D into distance with other 2D. One term. Next. Focus on conductor B. Distance with other D. Distance with other again D. Next. Focus on third conductor. Distance with other D. Distance with other 2D. The whole raised to again 6 terms will be there. 2, 1, 2, 3, 4, 5, 6. Raised to 1 by 6. So again if you do this, you will get 4 raised to 1 by 6 into D. So it is nothing but 1.26 D. And GMR will be same with nothing but R dash. It's nothing but 0.7788 into R. So if you have GMD and GMR, you just substitute in equation, my dear. L per phase equal to what? 2 into 10 raised to minus 7 ln GMD 1.26 D divided by R dash Henry per meter. So that is all about the two type of unsymmetrical spacing. Next we will discuss some more different pattern. Is it clear, my dear? Is it clear? Initially you may feel slight difficulty. Next type of unsymmetrical spacing. Three different conductor spacings, D1, D2, D3. This is also an unsymmetrical spacing now. So what will be GMD, my dear? GMD is equal to focus on conductor A, B, C. Focus on conductor A, distance with other D1, distance with other D3. Focus on second conductor, distance with other D1, distance with other D2. Focus on third conductor, distance with other D3, distance with other D2. Total how many terms? 1, 2, 3, 4, 5, 6 and by 6. That's all. No, nothing more, nothing less. GMD. GMR is nothing but again symbol R na, each radius having radius R na. So 0.7788. That's. This is another type of unsymmetrical spacing. Yeah, you can do one more thing you can do. D1, D1, D1. 2 D1 na, 2 D1, my dear. So, okay, I will step in one more step. You can write like D1 square na, D1 and D1. D1 square, D2 square, D3 square. Whole raised to 1 by 6. So, it will become D1, D2, D3 whole raised to 2 by 6, which is nothing but D1, D2, D3 whole raised to 1 by 3. And GMR is nothing but 17788 R. Is it correct, my dear? Is it correct? Okay, that's all. So this is one type of unsymmetrical spacing. And another type of unsymmetrical spacing, right angled unsymmetrical spacing, my dear. Right angle unsymmetrical spacing. Suppose this and this will be A, this is B and this is C. D and this is D, but this will be D root 2, this will be D root 2. So in between every 3 conductors should be equally spread, then only it is symmetrical spaced. If there is any one conductor and other conductor is not equally spaced, then it's called unsymmetrical. So this is also a type of unsymmetrical. So what will be GMD now? What will be GMD now? GMD will be focus on first conductor A, distance with other D, distance with other D root 2. Second one, second conductor, distance with other D, distance with other D. Next, focus on third conductor, distance with other D, distance with other D root 2. How many terms are there, my dear? 1, 2, 3, 4, 5, 6, so whole raised to 1 by 6. So it will become 2 raised to 1 by 6 now, plus D raised to 1 by 6, D raised to 6 now, 1, 2, 3, 4, 5, 6, the whole raised to 1 by 6. So simply 2 raised to 1 by 6 into D. That is GMD. That is GMD. So what will be GMR? Simply 0.7788 into R. So what will be L? L 2 into 10 raised to minus 7 ln 2 raised to 1 by 6 into D divided by 0.7788 into R. Henry per meter per phase. That's all. See, the analysis is very difficult actually, I know. But anyhow, you have to remember. No way. We have to remember and study. Mr. Clear? It's a clear, my dears. Is it clear? Okay. Next, symmetrical transmission. Inductance 3-phase line symmetrical. Symmetrical transmission line. Each conductor is separated by D, mutually equally spaced. Then what will be GMD? What will be GMD, my dear? Focus on conductor A. Suppose this is A, B, C is 3 phases. Focus on conductor A. Distance with other D. Distance with other D. Focus on B. Distance with other D. Distance with other D. Focus on third conductor. Distance with other D. Distance with other D. How many terms? 1, 2, 3, 4, 5, 6. Whole raised to 1 by 6. Simply D raised to 6. Whole raised to 1 by 6. Simply D, my dear. That is the beauty. If you equally spaced 3 conductor, then the GMD will be simply distance between any two. That's all. So GMR 0.7788 into R. That is no difference. So our L will be 2 into 10 raised to minus 7 ln D by R dash, simply Henry per meter per phase. That's all. That's all. Is it clear, my dear? Is it clear? Next, bundled conductor. Bundled conductor. See my dears, see my dears. Bundled conductor means instead of using a single conductor for one phase, this is for phase A and this is for phase B and this is for C. We are using a bundle of conductor in the form of triangle, square, hexagon, etc. We are using a triangle shape. Now this is a triangle shape bundled conductor. That means for phase A, instead of using one conductor, we use three conductors, each having radius r, and but it is spaced triangly in form of triangle. That means the three-dimension view like this, my dear. The three-dimension view will be like this, the triangular form. The triangular form will be the conductor. Okay, the triangular form will be the conductor. The sides are represented by L. The side of a triangle is nothing but L. So what will be its GMD? Its GMD. What will be its GMD, my dear? Its GMD. Focus on conductor A. Okay, fine. Focus on phase A, conductor A. Distance with other, it is D. Distance with other, it is 2D. Next, focus on second conductor, okay, B. Distance with other, D. Distance with other, again D. Third conductor, distance with other, D. Distance with other, D plus D, 2D. The whole raised to 6. So it is again 4 raised to 1 by 6 into D. This is nothing but 1.26 D. Okay, that is the GMD. That is the GMD. Then what will be GMR? What will be GMR? What will be GMR? What will be GMR? See, my dear, this is act as a single conductor, my dear. This is act as a single conductor. This is also act as a single another conductor. This is also act as a single another conductor. Okay, by suppose we are viewing from externally, you seems like it is a conductor, it is a conductor, it is a, but internally only it is bundled. Internally only it is bundled, my dear. Otherwise it's a single conductor. Otherwise it's a single conductor. Sorry. My allocation is gone, right? Just a minute. My tripod has. Okay, now it's clear now. Now it's clear. So, okay, now it's clear, right? I think it's clear now. Okay. Listen, my dear. So, by viewing, suppose we are externally viewing, it's a single conductor. Only inside only it is bundled. So, GMR will be, I will tell you now, GMR means self. GMD means with respect to other. That way you can think. So GMR will be, my dear, R means self radius. The other radius also there, na? Because this is a single conductor, na? So you have to consider this conductor and this conductor. So other will be, length will be L, other length will be L. That is the beauty. Next one. Same manner, see, other focus on this radius, because 3 phases, right? 3 phases means you have to consider for 3. So not this, again consider this. This is the conductor you considered, R into L into L. GMR means self, not other. So self means again this is another self, because these 3 conductor constitute a phase. These 3 conductor constitute a phase. So under a phase 3 conductors are there. So 3 are self. So this is 1 R. So R, another conductor distance L, another conductor distance L. Now again this is R, another conductor distance L, another conductor distance L, another conductor distance L. Again this is R, another conductor distance L, another conductor distance again L. whole raised to, how many terms are there, my dear? 1, 2, 3, 4, 5, 6, 7, 8, 9 terms raised to 1 by 9. Raised to 1 by 9. Did you get how we took the GMR? Listen, GMR means self. Initially the self was contributed by a single conductor. Now the self was contributed by 3 conductor, because these 3 conductor constitute a phase. So we have to include these 3 conductor in order to get a phase. So we have to consider its radius but also with other, because these 3 combine to form a single conductor, my dear. Here it is a single conductor, but instead of this, now this formed by with 3 conductors. These 3 are internally connected. So self consideration should be there for that. That's all. Is it clear? Is it clear, my dears? Did you get what I am going to say? Okay. So how can I do this? R into R into R cube raised to 1 by 9 into L 1, 2, 3, 4, 5, 6. L raised to 6 whole raised to 1 by 9. So it will become R raised to 1 by 3, L raised to 2 by 3. That will be GMR. So by bundling the conductor, my dear, we see what will be inductance L 2 into 10 raised to minus 7 bundle the conductor inductance. Ln GMD is nothing but, my dear, 1.26 D divided by GMR R raised to 1 by 3 into L raised to 2 by 3. What? Henry per meter per phase. Okay, per phase. So what happens to the inductor, my dear? Compared to the unbundled conductor or non-bundled conductor, what is the inductance value now? Now L increased because L decreased because 2 into 10 raised to minus 7 Ln D 1.26 D again there also 1.26 D divided by R dash only there, but now R raised to 1 by 3 into R, L raised to 2 by 3 terms increased, so that this denominator, what happened, my dear? Increased. Denominator increased means the L will be decreased. So L decreased means I into XL also decreases. So voltage drop across transmission line decreases and voltage regulation improved. So what are the advantages of bundling conductor, my dear? The one thing you can say that it increases the flexibility and reduces the sag. I will tell you in the later on classes what is sag and all. So to increase the flexibility, I know that, but more than that, the inductance value will be increased, so that I into XL drop will be decreased. If I into XL drop decreased means we will get a good voltage regulation, my dear. That means the drop across the transmission line goes decreasing, so that the voltage regulation improved, so that the voltage drop across the transmission line decreases. So that is the main peculiarity of, that is the beauty of, that is the main advantages of using bundled conductor in the transmission line. Bundled conductor in the transmission line. Is it clear, my dear? Is it clear? Next, transposition. See my dear, transpositioning means, suppose we are using A for very long time without transposing, B for long time, C for long time, meaning depending upon the distance between these three are again in the transmission line now we can't space, actually equidistance is not possible, or symmetrically is always not possible my dear, because there is a huge wind, the symmetry will break. There is suppose a bird sitting on the transmission line, symmetry will be break. There is one tree branches what is hit on the surface of the conductor, there will be again symmetry break. So the symmetrical distance is not always maintained in a transmission line, so always there will be the different inductance happens, so the difference voltage happen, there will be poor voltage regulation every time because symmetry is breaking every time. So in order to avoid that, what we are doing, for some distance this ABC arrangement, for another distance CAB arrangement, for another distance BCA arrangement. So what is the function or what is the useful of this means, suppose here A and C is unsymmetrical, now it is corrected here, A and C become symmetrical. Here A and B may be symmetrically spaced, but here A and B may be again symmetrical, but here A and B unsymmetrical. Here B and C may be equally spaced, symmetrical. Here B and C may be unsymmetrical. So every unsymmetrical in some section will be compensated by symmetry in the another, again compensated by unsymmetry in the another. Likewise, symmetry, unsymmetry, symmetry, unsymmetry, always what? Mixed together, so that overall performance, in the sense overall inductance will be again reduced compared to the unsymmetrical spacing. That is the function of a symmetrical spacing, that's all. So what is the purpose of symmetrical space means, function of symmetrical space means, how can we say, unsymmetrical inductance can be avoided to avoid communication or interference with neighbor line. There may be a communication interference with another line, so that also may be compensated in each after equal interval of time. That's all. That is the function of the transposition, my dear. Okay, that's all. So that's all for today's session. So if you have any doubt, please comment in the comment section. So thank you so much.